Okay, I'm going to talk about retrieval augmented generation and not with a vector database. Many of you will have heard of retrieval augmented generation, and there's an assumption out there it's always related to vector databases, but I'm going to talk about doing retrieval augmented generation using tabular data, so data that's in tables. And as you know, most enterprise data is in tables. It's in the data warehouse, it's at the lakehouse or databases, operational databases. And tabular data is really the holy grail of RAG. There's a holy grail. We are in London. This is a Python conference. So those of you who are of my generation will get the reference. There's actually a West End musical on Monty Python as well as a walking tour, if you're that way inclined. And there will be a few Easter eggs in the talk, so keep an eye out for them. Okay, but I'm going to talk about function calling, because that's the question we're going to use. Sorry, there we go. That's what we're going to use to actually do retrieval augmented generation for tabular data. So let's introduce RAG first. I'm sure many of you will have heard of RAG, but bear with me while we're here. LLMs, as we know, are trained on massive amounts of data. And what they do is they build a model of language, and by implication, a model of the world. And Ilya Sutskever, who's been the main person, I would say, behind the renaissance of, well, not renaissance, I mean, it's really the first coming of LLMs. He basically claims that next token generation is enough for AGI, right? That being able to predict the next token requires not just a model of language, but how the world works. Now, we know that LLMs are trained on a fixed amount of data, and they have a cutoff time. So when they have a cutoff time, Llama 3 is a model that Meta released quite recently, and had a cutoff time. We can see there that the training data stopped in the 8 billion model in March 2023. And the 70 billion model was in December 2023. So if you ask it a question like who won the table tennis championship last year, and it was Germany for the women and Sweden for the men, I think this is a European one, it doesn't know the answer because its training data only went up to, in this case, March 2023. So what RAG is really about is getting external data into the prompt. So the prompt is when you ask the LLM a question, you're going to write some question as text. That's what we call a prompt. And what we can do is we can get lots of examples of text, put it in the prompt, and the LLM will be able to reason about the answer. And that's where vector databases have been quite widely used, because you can take your prompt, which is a string, and ask for similar pieces of text from your vector database. And they're very good at doing similarity search or approximate nearest neighbor search. They're fast, they can store lots of data, and you've seen a lot of good demos with them. One of the issues, there are a lot of issues with it. I'm not going to go through all the issues, but they are quite probabilistic. But I'll get through the main issue, which is that they're not connected to enterprise data. We'll get to that in a minute. So our query comes in, we build up the prompt, we retrieve these chunks of text, we put them in the prompt, we ask the question to the LLM, and it gives us back a response. And in this case, if we had some text related to the European Table Tennis Championships, it would hopefully find the related text, put it in the prompt, and the LLM would be able to tell you who won it. And that's great. We've seen a lot of demos on that. But what I'm going to talk about is function calling as a mechanism to retrieve data from tabular sources. And function calling is the most unfortunately titled term for LLMs, because people think the actual LLM is making a function call, but it's not. So a function calling LLM is really an LLM that outputs JSON. So well-formatted JSON. So you put in a prompt or a user query, the LLM has been fine-tuned to return JSON output, and that's what it is. So a function calling LLM returns well-formatted JSON documents. The great thing about Python, as we know, is a dynamically typed programming language. We can take a JSON that's returned that represents a function. It could be the name of a function, and then we have parameters of the function. So then we can call that function by parsing the JSON and then invoking the function in Python. And that's what we're basically going to do. Now, not all LLMs are suitable for function calling. There is an interesting leaderboard that Berkeley update, and that's called the Berkeley Function Calling Leaderboard. And you can see at the top we have GPT-4, Claude 3. Some of the open source ones we can see, Meta Llama 3, 70 billion at position number 9. And the 8 billion is quite a long way down, and its overall accuracy is not great. Now, the important point to point out here is that what is the benchmark testing? Well, it's not just testing functions that we're going to use to retrieve tabular data that I'm going to talk primarily about. They're about all types of functions, because a function could send an email, it can look up, make a REST call, get some external service, execute an action. So they have a very broad set of functions that they're testing in this benchmark. And they don't test all models. So the one that we like to use is at the bottom. It's a smallish model. It's a fine-tuned version of Llama 3, 8 billion, called Hermes. So some of you may have heard of it. It's extremely high performance. I think it's somewhere to 80 to 90% on the accuracy in this particular leaderboard, but it's not there at the moment. So these function calling LLMs will enable agentic workflows. So Andreang is going around talking about agentic workflows a lot. And we're able to make API calls, perform tasks by the LLM. But I'm going to talk primarily about using these function calls to get our tabular data. Now, RAG exists within, I mentioned that we get fine-tuned LLMs for function calling. But you do have to consider them when you're looking at building your first LLM applications. You start typically with just prompt engineering, see if you can get that working. And then if you can, you can maybe progress to RAG. And then if you're happy with that and you want well-formatted output of a particular structure, you can fine-tune your data. So our large language model gives us a model of the world. You may have private data that you need to fine-tune on. And then we need this external data. So there's real-time history and context data. And that's what we call RAG. And I mentioned already, people primarily associate this with vector databases. So we're going to do approximates nearest neighbor search with the prompt, and we'll get back some response. The elephant in the room here, I mean, there's a lot of vector databases out there that have raised hundreds of millions of dollars in venture capital. I don't think that the existing database tables in the data warehouse and in relational databases are going to be copied to vector indexes. It doesn't make that much sense, right? So if all of the valuable enterprise data is in the data warehouse, or most of it, I won't say all of it, but a lot of it is in the enterprise data lakes, the data warehouses, the operational databases, will that data end up in vector indexes so we can query it for RAG? And I don't think so. I think what's going to happen instead is that we'll have a different way of getting the data. I'm going to talk about function calling for that. But you may say, well, why don't we go directly to SQL instead of function calling? So I'll get to SQL in a second, but I'll give you just one insight before we get to SQL. There's an assumption in RAG as well that the only data available to you to retrieve external data with is the prompt or the query, what the user entered. But that's not true. So this is an important insight, because when you build an application, your LLM will be embedded inside some application. So it says LLM-powered application. You probably logged on to the application, or maybe you entered in a booking ID on a retail site, or an order ID, or there's a session ID. There is some identity associated with that application. That is the key that will unlock the data in our data warehouse and data lake. So that's the first insight, that you have to have these keys. And the keys that are available determine what kind of data you can retrieve and how much RAG you can do. So what we're going to do is use these keys, or IDs, we'll call them, as well as the questions themselves, to make queries on the database. And that's what we're going to do in the rest of the talk. And I work for Hopsworks. We provide a platform that has a feature store. We have a booth outside, and we do model serving, so it's like a full MLOps platform. And this is what like a complete system would look like. And I'll break it down in a bit. You'll ask your question. The question gets sent to the model. The model will use function calling to execute a database query. It'll get the results back, number 3 and number 4, and then it will pass the results to the actual model, which will generate the response, and that's we'll get our response back. So there's going to be 2 calls to the LLM. One to say what function should I execute, then we're going to execute the function, and we're going to get the data back, and then we're going to get another call to the LLM to get the response. Now you may think that, well, why don't I just go straight to SQL, go for my text and generate some SQL. It's hard, right? There's a lot on this slide, but LLMs are not really that close to solving text to SQL yet. So at the very bottom of the slide, you'll see something called the BIRD benchmark. So you'll see teams like the BigQuery team are trying to really, see if they can solve this problem. We're at about 65%, 67%. It's not really near good enough to be able to generate reasonable queries. So if you have a query, I have a table here called loans. And we can see there's lots of columns in the table. Some of the columns are human readable and understandable. Most of them actually are. But you could probably issue D_D. It's not that clear. You can see from the text that it's a date time, but you could probably make it a bit clearer, because what we want to do here is we want to have a lot of metadata to tell the LLM about the different columns that are available, what they represent, what's stored in them, and we're going to use that information to give the LLM context with which it can decide, oh, that's what I need to execute, that's the function I need to execute, or this is the column that I need to give the answer about. So I have a question here, how much money did I borrow in the last 10 years? The SQL query for that question is select count on the loan amount column from loans. So I need to know that's the column that I'm referring to. I have an aggregation here, the count, and I'm going to use it for my identity. So that's the ID is going to come in. It's going to be my identity that's injected in here. And we know that it's 10 years ago, and today's date is the 15th of June, 2024. So we go back 10 years in time. So the LLM has to answer questions like, okay, which is the table I want to go to? Or is it a set of tables? It needs to know what each column means. It needs to know what type of operations or aggregations or filters or joins to perform. It's a really hard problem. So how can we make this a little bit easier? I'll go jump to the UI to show you what this looks like. This is Hopsworks here. So we have tables. We call them feature groups. They're basically tables of features. And this one is the loans table that I showed you. And we can see that each column here has a description, right? So we have a description, we have type information. So this is a lot of metadata that we don't have in a typical database. So a typical database wouldn't have descriptions, metadata for the columns. We can go in and, of course, edit this if we want to. I can go in and edit my descriptions if I think they're not correct. You can, I saw Ali Ghodsi do a demo last week to basically infer a description of a column. Now, you could do that. It's kind of like writing production code by inferring types in your pandas data frame. It's happy at the beginning, but it all ends in tears. So typically, you kind of want to do this by hand. You want to give it as good a description as you can. So this particular table here, this loans table, we can augment it with a lot of metadata which our LLM will be able to use to decide, okay, they asked about how much they spent in the last 10 years, or how much money they borrowed, sorry. I know that that's loan amount because they borrowed money. I need the amount. It says AMNT here. You might want to rename that column to call it amount. So one of the things people do in Hopsworks is they have an existing table in Postgres or in MySQL or Oracle, and they mount it into Hopsworks as a feature group. And then you can rename the columns, and your original data stays in Postgres or MySQL, and we just then send the queries back down there. So we translate from the new column name to the old column name. So that means you can keep your data as it is, but you can have the human readable descriptions in we call that an external feature group in Hopsworks. So here you can see I just added some descriptions to the different columns. Hopsworks also knows about index columns. So these are special columns. Databases, many of you will know, have things like primary keys. You also have indexes. You also have foreign keys in databases. So in this case, we have a special column in Hopsworks called the event time column. So most feature groups will have an event time column. When we're training models, often we're training on time series data. So loans, you can see they have a timestamp when the loan was issued. And this is great because now we know that a feature group will have a certain structure. We know that there's a primary key and we know that there's an event time column. And we can actually use that information to generate two queries on every feature group. So this is what we do. We basically say, any feature group you have, these two queries can be extracted from it. One is, get an entity for a specific event time. And the other one is get an entity, get the data for an entity, I should say, for a range of time. Okay, so obviously I've put in the concrete types here, int and so on, but this gets injected in depending on the primary keys in your feature group. And it may be a composite primary key with multiple columns, not just a single column. But the timestamp here is always a single column. So it's not like a data warehouse where you have a start time and an end time column. We'll always have a specific timestamp value. So this is just showing you roughly what happens. Like this is the query that gets generated. It's slightly more, it's more complex than that, but at a high level, every feature group will have these two functions available. So these are what we call pre-canned queries. We're going to get just data related to entities. We can't do, this is quite limiting in terms of the data we can return. You can do a lot with it. So let's take the question we had earlier. How much money did I borrow in the last 10 years? So the way that will work is that the prompt to our first LLM call, the function calling request, we'll say, here are my functions that are available. There will be more data in the prompt related to the description of the functions and so on. And then you have your actual query. How much money did I borrow in the last 10 years? The function calling LLM will either say, this is the function to call with the parameters, or it will return and say, I can't find a function to call. In this case, it finds a function, get entity data for time range, and then you have to invoke that function, and you'll get your results. And with the results, which will be the rows that are returned, you basically make another query on the LLM. And you say, look, here's the definition of the table, here's all the metadata related to columns and so on. Here are the results, right? So put the rows in there, and we know which columns they are for the rows. And now if you ask the LLM, how much money did I borrow in the last 10 years? The LLM is going to do the count for you. Now that's a bit scary. It's going to do the aggregation. I'm not going to make promises that they will never hallucinate. But it's, depending on the types of operations, this is where LLMs will get better over time because this is what people care about. This is a specific hallucination that people are worried about. Okay. So to summarize, to put all these steps together, the generic model, I gave a specific example for the loans table, but the generic model is the following. We have to have some IDs at the beginning, some sort of key to unlock the enterprise data. We'll always have the user's query, and we're going to query the LLM to find out what functions are available, because we may have many feature groups, many tables. We're going to pick the right ones, and see which one it wants to execute. Now, the LLM will return the function to execute in the parameter values if it finds one that's suitable. We'll run that function on the tables, execute it, and then we'll add the function results to the prompt, send it back to the LLM, and get our results. And this one is, duplicated here. This should be the results will get returned to the client. Now, I did mention that, if you have your tables on a different database and you want to do this, well, we can just mount them then as external feature groups, and that's the way to do that. Okay, so that's kind of the model that I'm presenting for it. Let's move on to a slightly more complex topic, which is, well, I've got data across many different tables, and if you're just going to call individual functions for different tables, I would like to have, I know for this specific model or this problem I have, these are the columns I need from these different tables. And the LLM just won't be able to figure that out. So in databases, what we often do is we create views from tables. So if I say, these are the particular columns I want from all of these different tables, I can create a view. Now in HopsWorks, this is the point here. So we don't want to, we want to make as many tables and data available for function calling as possible. So in HopsWorks, you can create a feature view from these feature groups, and I'm switching track to a different data model. This is now air quality, because, well, I have I'm going to do a demo on air quality, that's why I'm going to move to it. So in air quality, we have two tables. We have the measurement of the air quality. It's something called particle measure 2.5, and then you have a timestamp from when it was measured and the location and so on. And then we have weather. So weather is very good for predicting air quality. So you have the wind speed, wind direction, temperature, precipitation, and we can use those features to predict air quality. So I can create a feature view which joins columns from those two tables together, and this is how you do it in Python. So you don't need to be a database expert. You just write some Python code, you run the code, and then you're going to get your feature view. I'll just show you what it looks like here. So this air quality project here. So these are my two tables. You can see air quality here. We can have a quick look at the data inside it. See how much data. We've got quite a lot of data in here. That's quite a lot of data. And then we have the weather data here as well. So this is our weather data from many different cities. And this is, by the way, the third chapter in the book. If you want to try out this demo, you can train a sensor. You basically pick a sensor from anywhere in the world. There's tens of thousands of them. And then you train a machine learning model to predict air quality at that point. And it'll draw a dashboard, and there's even LLM powering to ask questions on that model to say, well, what's the air quality going to be like next week? I'll show you that in a minute. But that's in the book. Okay, so we have these two tables. We want to create our feature view. And this is the feature view that got created from our Python code. And you can see it looks very similar to the feature group, because it is. It's basically just the tables. We can see the tables and their columns. So this one is the air quality table. The column is PM25. And if you go further down, we'll have some features from the weather feature group. And we can see we have our primary key and event time as well. So we can issue exactly the same queries. We can generate the same functions that we want to use to basically query that table. Now, some of you will know, who are database folks, there's probably not that many database people in the room, and this is very technical, a very technical point. And I'm going to change to a different problem, because we're just jumping around. Their tables are tables. Imagine I have a different problem, and this is a common problem we see in machine learning. I want to predict credit card fraud. Right? So credit card transactions, if we're looking at processing them in real time, what happens is the transaction will come in with a credit card number. We'll have the merchant ID, whether it's maybe online or offline. We'll have the amount of money spent, the location, longitude, latitude, and the category. That's it. That's all the information you get. It's very light, right? You can't train a machine learning model to predict credit card on that. I think we can agree. So what typically happens is that people will write pipelines to compute features that are predictive of credit card fraud. So how many times has the credit card been used in the last 15 minutes, last 30 minutes, last day? How much has been spent? Where was the last location the credit card was used? Where's the current location? So a geographic attack. So these get pre-computed. So typically you would have a feature pipeline or a streaming feature pipeline. We've got Quicks and Wax here who can do that for you. And that data is then stored in a platform called a feature store. And we can then retrieve those features at runtime. And then we get lots of features that can actually predict credit card fraud. So how do you retrieve those? Well, we use these feature views to retrieve them. So we can use the same mechanism, the feature view, to basically retrieve RAG data at runtime. So in this case, you have to always ask yourself, well, what are the IDs I have to get the RAG data? Because the ID is the key thing. And in this case, for a credit card, we've got two IDs. We got the credit card number and the merchant ID. Now, when you were looking at the credit card fraud problem, you realized that, well, if it's a virtual credit card or a bank-issued credit card, that's very indicative of fraud. I'd love to have information about the issuer of the credit card. Or you might say the user's bank account. If the user has a mortgage, then it's highly likely that it's not fraud. They're kind of a good person. So what keys you have available and what data you can get back is the issue. Now, to answer that question, you actually need to know something called what type of data model you have in the back end. Is it a star schema or a snowflake schema? And our character here from Monty Python didn't know the answer, so he was thrown into the abyss. If you remember Monty Python, the quest for the Holy Grail. So with the star schema, the problem we have is that we have features that we know are great for predicting fraud in the user's account and in the credit card issuer table in the bottom left, but we're not able to use them because we don't have those keys. Now you could argue, well, I could write a mapping table and keep them up to date, and then we could look that up and so on. In real time, you typically will have an SLA, and then maintaining all that code would be a nightmare. So the answer to do this is actually to change your data model. Don't use a star schema for this, use a snowflake schema. Snowflake got their name, by the way, from the snowflake schema. You can see it's chained. We have, from credit card transactions, we have a foreign key to the aggregated credit card transactions, and there we have two more foreign keys down to account details and credit card issuer. So with a snowflake schema, you can now retrieve more data, more features to get better RAG in this case, but also for any model in general with an online feature store. So what's the point of this? Well, the point, of course, is that Hopsworks does this and no other feature store does, of course. All right, so we spent a lot of work doing this, and I think we're the only ones who do this at the moment. So I'm going to talk a little bit about Hopsworks. That's our platform and how we build these kind of systems, the ML lifecycle. So Hopsworks is a kind of a platform for making it easier for you to build and operate AI applications. And the model that we typically present for people to build AI systems, not just training a model or creating features or making predictions, is what we call the Feature Training Inference Pipeline, or FTI pipeline for short. So typically, we recommend people to organize their AI systems as 3 sets of pipelines. These are groups of pipelines. Now, you can have specialized pipelines within them. You could have like a training data set creation pipeline, which would be part of the training pipeline. But in general, this is enough for you to have a great model for teams to collaborate in building AI systems, because this model is a unified model for batch, real-time, or LLMs. So depending on whether you're building a batch model or a real-time model or an an LLM system, this architecture will work for all of them. And that's great, because if you've been hacking out a batch model, it may be very challenging for you to move from what you built, the big monolithic batch system, to a real-time system. You're kind of going, how do I relate the two together? I teach a course, by the way, at KTH, and students build systems with this architecture in 2 weeks. They build complete AI systems. They have to specify a non-static data source that keeps producing data. So they have to write a feature pipeline to get that data. Then they have a training pipeline to train their model. And then they have to have a batch or online inference or LLM system to make predictions and have a UI. So if you're curious, you can just Google that and you'll find there's about 100 of those types of systems out there. So you basically write these 3 pipelines. The feature pipeline takes your data in and it outputs features or labels. And in the case of LLMs, we may take text. If we're doing RAG with PDFs, we might chunk it up and write it to our, you might say, well, I'm going to write it to my vector database in Hopsworks. We support a vector index on these feature groups. So you just write it to the feature group as you would do to a normal feature group. And then we index then that column as a vector index, and you can do similarity search on the feature group. The training pipeline will take imagine we're staying in the world of LLMs, we'll have created a training data set, so we call it instruction data set for fine tuning. We may have used a trainer model to do that. We'll fine tune our LLM, and the output will be a trained model that we'll save. And then finally, the inference pipeline will take our trained model, and it'll take the new data that we want to make predictions with, and maybe we've got RAG data coming in here as well, and we'll make our predictions. So this is what we provide, so that makes your life easier. We provide all the infrastructure underneath. We have these feature groups that I mentioned. You can have the external feature groups. We have the feature views, and there's a model registry as well as model serving with kserve. And the model registry is designed with our file system, so you can save models that are hundreds of gigabytes, because it's just writing to the equivalent of an NVMe disk. And a lot of the model registries that are there today have REST APIs. You can't upload a fine-tuned LLM that's 150 gigabytes via REST API to MLflow. It just doesn't work. Okay, so let's move on and look at, before we do that, let's do a demo. Right, so let's have a quick demo. I've just run this notebook earlier. I'm running it on a Hopsworks private cluster, so I wanted not to use OpenAI. I have OpenAI at the end, but I think it's more interesting to use these fine-tuned smaller models that run on a single GPU. So in this case, I'm using Hermes, which is the fine-tuned model. And if we zoom in a bit here, I'm using LangChain to generate some questions. So this is the air quality example I said before. Now there's another detail here that I can also do function calling on my model. So if we go to my air quality example, I have a model down here as well. This is the model that I trained. And this model will predict air quality for lots of different locations. We've got some performance metrics on it. I didn't upload images here, but I do have some images in other examples. But with this particular LLM, I added a couple of functions to call the model as well, because we can do that. We can say, okay, if it's a future, if I want to know the air quality in the future, it's not going to be in my table. The table only has the historical measurements. If it's in the future, I'm going to ask the model instead. So we can do that as well. So function calling is kind of flexible. So here we can see a question: what's the air quality from 10th of January to the 14th? It gives us some measures of the air quality. This is what we get put in the prompt, and then it gives us this interpretation. So it was generally in the safe range, which is correct. And then it gives you a little bit more details. If we jump through some of these down here, we see air quality in London yesterday, and it said, yeah, it was moderate. PM 2.5 was 15, safe to go for a walk. These are mostly historical. What will the air quality be like next week on 20th of June? So in this case, you can see it didn't actually call the correct function. It called the one in a time range. It should have called the point in time one. It gave us back the dates though, so it was able to actually infer, oh, the air quality would be quite poor. It's slightly, to be honest, it's hallucinating a bit here because that air quality is not that bad. And then we can ask, tomorrow this one worked correctly, called the correct function, and so on. And I had an example with OpenAI, just to show you it's the equivalent in OpenAI. And I asked air quality like tomorrow in Chicago, and it gives us an answer there. So that's basically it. But let's go back and look at, so I'm not against, right? So the first thing, I'm not against vector databases. Vector databases have an important role to play. I call them vector indexes because I think many of the people will be using vector indexes on existing databases rather than having a dedicated vector database, but that's just my opinion. But we can superpower vector databases in RAG with function calling. Let's have a look at an example. This is something we built. It's available on our tutorials, by the way, if you're interested. All of this is open source code. These notebooks are available, HopsWorks tutorials. But in this case, we built a system to query PDFs. So you put your PDF documents into a Google Drive, and then we have a feature pipeline which will take those documents, it will chunk them, and it will write them to the feature group, okay, with the vector index enabled. So now you can ask questions about the documents. In this case, they were regulations. And you could say, well, tell me about these regulations in the docs. And this is our prompt. We get all of the closest chunks to the question you asked, we'll put in the prompt here. And because we used our vector index to get those back with similarity search. And then the LM will give us an answer that here's the, your question was about regulations, here's the answer. The problem with this is that there's no personalization here. We actually talked to some large enterprises about this, and they said, well, the way we're set up, this is how we're set up. We have all of these regulations, we have all of these business units, and they're all affected differently by different regulations. So there's no one set of answers to everyone. And you could, of course, train different, you could create different indexes for all of the different business units, but it would be a very complex thing to do. What's easier to do is to basically use function calling together with the vector index. So we can, this is our data model here. We can take a user, take the user ID, and then find out which policies and regulations and requirements affect this user, and we put them, inject them into the prompt. So now we can personalize our LLM using the data in our warehouse. So what this looks like is the following. You ask the question about the data. We use function calling to get back all the regulation information, and then we can put that in the prompt along with the chunks that get returned. We can actually also use that data to go to the vector database as well to get better responses from the vector index. And now we've got a personalized RAG enabled by function calling. So just to recap on this, we looked at function calling for RAG. We looked at this particular architecture here where we've got a model of the world. We're looking at RAG, and we use function calling to get our data from the database tables. And what we did with HopsWorks is we kind of layered these abstractions that we have in HopsWorks on top of this model of the world. We have training pipelines for fine-tuning, inference pipelines for RAG. Oh, this doesn't show up very well at all on the screen. And then we have the feature groups and feature views where we can retrieve the structured data, but also do the approximate nearest neighbor search on. And then feature pipelines which feed the data into those. And this is what HopsWorks looks like. HopsWorks doesn't run the pipelines. You need to run them yourself. You can run them on HopsWorks or on any external platform. So if it's Spark or Flink or Python or Pandas or Bytewax or Quix or any of these frameworks, you can run those. And they'll access the three different main APIs, feature, training, and inference APIs. And then we basically provide the infrastructure that you just then have to work on these ML pipelines. So that's it. If you're interested in learning more, there is a book with a few chapters that are already out. You can get access to it. I think the first two chapters are free at least. The book isn't finished yet, I will admit. And if you have a more academic bent, we had a paper at SIGMOD last week, which describes our platform in detail. Also tells you how we're between 40 and 15 times faster than GCP, Databricks, and Google Cloud, if you're interested in that. And there's also a community, a serverless ML community and a HopsWorks Slack where people are building these AI systems and they're sharing the systems, and you can go and join it there. HopsWorks is available as a serverless platform with 50 gigabytes of free forever storage, so you can just pip install HopsWorks and start using it today. And we will have a Kubernetes version of the platform out next month, so you'll be able to just spin it up in your own Kubernetes cluster if you want to try it out that way as well. That's it. Thank you.
Thank you.